Welcome to yet another video in our cyclic geometry series. Our first theorem in this series was that an angle at the center being twice the angle of the circumference. And then we did a second property, which was the property on angle in a semicircle being 90 degrees, followed by angles on the same segment being equal. Went further to do other properties, including opposite angle of a cyclic quad, that was episode number 5, and then the exterior angle of a cyclic quadrilateral being equals to the interior opposite angle, that was our episode number 6. And then we also did the property on tangent being perpendicular to the radius. Next one, which was our last video, we talked about a line drawn from the center to the midpoint of a chord being perpendicular to the chord. So in this lesson, we are going to explore another theorem whereby we want to explore the relationship between two tangents that are drawn from the same point to the same circle. If you are drawing two tangents such that they are meeting at the same point called an external point, what's really happening on that one? Let's go straight to GeoGebra to define some stuff here. So we are here on GeoGebra. Now on GeoGebra, let's draw a circle. So to draw a circle, this is our circle like that, and then this is a circle. Let's draw to a point outside the circle. Before the point, let's draw the two tangents. One tangent will be from point B, the other tangent is going to be from point C. So on point B, there you go, that's our tangent. Similarly, from point C, that's our tangent. So this point where these two tangents are meeting is what we call the external point. Now that's our external point. Just a reminder, a tangent is a line that touches a curve or a circle at exactly one point. So this is our tangent going to point D, and that is our tangent going to point C. So we have got two tangent BD and tangent CD. What we want to explore is the relationship between BD and CD. Let's check them in terms of length. What's the length of tangent CD? That's 14.74. And then what's the length of tangent BD? 14.74. So this is our theorem for today. Let's try to play around. Hope you are noticing that they are equal. How if I take point C somewhere there? As you can see, these tangents are being extended, but still they are equal. So if you draw two tangents from the same external point, they are going to be equal. So that's our property for the they. Now let's try to write it down. Two tangents drawn from the same external point are equal. Maybe so that this thing can stay in your mind. Let's try to put a drawing here. Say that's our circle, and then we have the two tangents, one from here. Now there you go. Most importantly, this is what we call the external point. That's the external point. And And then this is the point of contact where the tangent meets the circle, and then you have the center in there. So if these two tangents are starting from the same point to the point of contact on the circle, they are going to be equal. This one is going to be equals to that. Now, let's check a few examples on this theorem or rather property. Now, there is our examples. The first example there, it's saying in the circle below, O is the center, PA and PB are tangents from point P. Now, if PA is equals to, if PA is equals to your 3x plus 2, this is your PA here. This is PA. And then you are told that's 3x plus 2. And then your PB, this is your PB. It's 5x minus 6. Then what is the value of x? How are you supposed to find x from this one? So to find the value of x in this one, all you are going to do is to recall the theorem. You have an external point P, and then these tangents are starting from the same point. So what's happening here actually is that tangent PA is equals to tangent PB. What's the reason for this? These are tangents from the same external point. Then from there, what's the size of PA? 3x plus 2. It should be equals to the value of PB, which is 5x minus 6. And then from there, let's solve for x. So to solve for x, let's take this 3 to the other side. Or in other terms, let's use 3 subtracting 3x on both sides of the equation. So if we do that, these 3x are cancelling out there. These ones are getting cancelled. And then you are left with 2 being equals to 5x minus 3x. It's giving me 2x minus 6. Then from there, we need to remove this minus 6 here. What are we going to do? Since it's minus, so you're going to do plus 6 on both sides of the equation. Algebra works on balancing. So what you do on the left, you are supposed to do on the right. So it's plus 6. What does that actually do? These 6 are going to be cancelled out. And then this side on the left, you have your 2 plus 6. 2 plus 6 is giving me 8 is equals to 2x. Then from there, divide by 2 on both sides. Then your x will be, your x is going to be 8 divided by 2, which gives me 4. So that's the value of x, 4 units. Next question, or rather next example. In the diagram below, O is the center. AB and AC are tangents to the circle. Angle OAC is 30 degrees. CBO. There was a typing error here. 30 degrees is not OAC. It's actually BAC. This one they are referring to angle BAC. angle BAC. This is the one that's equals to 30. As we can see in the diagram here, it's the 30 degrees. We are required to find x there, which is CBO. Now, how do we go about finding the value of x? First things first. Our property of the day is saying that once you see two tangents from the same point, now the same point in this case, it's point A, and these tangents are tangent A, B, together with tangent A, C. If two tangents are starting from the same point, they are going to be equal. This one is going to be equals to that in terms of length. Now, once two sides in a triangle are equal, that implies that that triangle is an isosceles triangle. Now, once we have an isosceles triangle, we are definitely expecting the base angles to be equal. So these two angles are actually equal. Now let's give them a name. Let's call them y. Let's call this one y and this one y. Now let's go to find the value of y. Since CBA or triangle ABC is a triangle, now the sum of its interior angles should be 180 degrees. So y plus 30 should give me 180. What is the reason for this? Sum of the interior angles in a triangle. Now y plus y, it's 2y plus 30 is equals to 180. Now let's do minus 30 minus 30. And then if we subtract 30 on both sides, these two are going to cancel out. Then on the left, you are left with only this guy here, which is 2y. So your 2y is now equals to 180 minus 30. That is giving me 150. And then dividing both sides by 2, you are going to, let's do the division here. This is over 2 over 2. Then your y is equals to 150 on 2, it's 75 degrees. Now, this simply tells us that here where I placed y is actually 75 degrees. 75 degrees. Now, if those are 75 degrees, we've covered a theorem from our previous videos on episode number 7, whereby we said that once a tangent meets a radius, there is going to be a 90 degrees. So in our case, this is a radius. It's meeting a tangent. So this is actually 90 degrees. So if this is 90 degrees, then the value of this is 90 take away 75. So your x is going to be equals to 90 take away 75, which is going to give us x is equals to 15 degrees. That's the value of the required angle there. Now let's do our last example for this theorem. Now in the diagram below, O is the center, AB and AC are tangents to the circle. Angle OAC is 25. Calculate CDB. Calculate the value of H there. Now, where do we start? The property for today is tangents from the same point, same external point. Now, our external point, our common external point is point A. So from point A, we've got this guy here. That's a tangent, and then that's a tangent. So what does that tell us? Since they are starting from the same point, they are definitely equal. This one is equals to that. Now, where do we go to from here? And then also, this one, OB is a radius. OC is also a radius. Now, triangle OCA and triangle OBA are actually having equal sides. They are congruent. What does that tell us? It says as that its corresponding angles are also equal. If the corresponding angles are also equal, then this guy here should be 25 degrees. If that's 25 degrees, how then do we find this angle here? How then do we find this angle here? Or another way to find this one is to say this one, there is a radius meeting a tangent. There is 90 degrees here. The radius is meeting a tangent 90 degrees. Just like that. Then this is 25. So this angle should be 90. Take away 25. And that's going to give me 75. Sorry, it's 65. So this is 65. Now, since this triangle is congruent to that, this one is also 65. And if you combine, but it's giving me 180. Now, this is the angle at the center. Twice this angle. 2 times this one will give me 65 plus that. So this angle is 65. Now let's write the proper presentation for this one. With angle OCA being equals to angle OBA being equals to 90 degrees. The reason tangent is perpendicular to radius. Then if we know that this one is actually 90 degrees, so to find this angle there, OC, it's COA is equals to 180 degrees. We are taking away this 90 degrees. We are taking away 90 and also taking away 25 degrees. Why are we doing that? Sum of interior angles in a triangle. Then that is telling us that COA is actually equals to 65 degrees. Now, what we've also noticed here is that the tangents are starting from the same point. So CA must be equals to BA. The reason those are tangents from the same point. Then we can say that triangle OCA is congruent to triangle OBA. The reason for this one is that it has equal sides. The corresponding sides are equal side, side, side. Then from there, y was happening with our 65 degrees there. COA is equals to BOA equals to 65 degrees. What's the reason for this one? Triangles OCA and OBA are congruent. Then from there, we have our angle at the center COB. COB is actually equals to 2 times 65. We're just adding those two angles, which is going to give me 130 degrees. Then from there, let's find the value of angle X. So 2 times X is equals to angle COB. Why are we saying that? Angle at the center is twice angle on circumference. Then your 2 times X should be equals to COB. It's 130. Dividing both sides by 2, you are going to get 65 degrees, which simply means that here we are having 65 degrees. Well, that was our theorem, or rather property, whereby we are saying that if two tangents are drawn from the same external point, they are going to be equal. Now, our next lesson, we are going to be talking about the term called theorem. Please stay on the channel and then keep your notification bell on so that you can be updated on when the next episode is going to come up. Stay tuned for more. Thank you.